we've seen that z equals x plus iy. Lines of constant x and y are great. Because this physically describes a lot of circumstances in fluid flow and electrostatics. And clearly del squared x equals del squared y equals 0. It turns out we get another one kind of for free, actually. So if I choose to represent this in radial form, and if we have enough time, it's going to get close. I'll show an example of that. So how to actually find the potential of Earth, because Earth is not a sphere. It turns out people lied to you. They always do. Earth is a prolate ellipsoid. So it's spun out a bit at the equator. So you can still start with z, and z still satisfies the Laplace equation on both its real and imaginary parts. But we have r equals constant, and oops, do that way off. So r equals constant would be these rings, and then theta equals constant, or phi equals constant as I've written it, are these lines. And this looks like gravitational field lines and gravitational potentials. Okay. So those are both good places to start with, good inputs. So the other thing is that you can kind of chain these together. So if it turns out if I have 10 different analytic functions, and I have f of g of h of p of q of z, I go nuts if I don't do that correctly. 1, 2, 3, 4, 1, 2, 3, 4. That actually this is a solution. The real and imaginary parts correspond to a solution of Laplace's equation as well. So you can just chain these together. But these are two really good starting points, because these definitely look like the potentials of spherical charged or gravitational massive object, and these look like parallel plate capacitors or the starting fluid flow of a wind tunnel. So the input, you get something else beyond what we've discussed if you just think about polar form. So now as far as the output goes, you have two tools. You have intuition about f of z's, and I just want to give you a handle on how you want to think about what they're doing, and we'll solve wind going into a corner, so wind blowing into an alley, or if I took a parallel plate capacitor and I bent it at an angle, like a 90-degree angle, you can do that by hand. And then secondly, this was really important, so people have dictionaries of conformal mappings. So first, the intuition part. So state it this way. Okay, so f of z equals z squared is analytic. And what I'm asking is, I only give you guys points, and I have inexhaustible patience in the upper half plane of the complex plane. So we can sit here and do this all day, where I pick points out of the upper half plane and I give them to you, and I want to know where those points land in the image of all of the things. So we'll call this the z plane. And this is kind of the traditional way of doing this. And we'll call this the W plane with W equals f of z. So I'm only feeding you the red region, and I want to know where it lands in the complex plane of all of the possible outputs. So maybe some math helps, but probably shouldn't have to do too much. There's a really important key insight. We've been using rectangular expressions and the rectangular form of complex numbers basically exclusively. And in this case, it might be helpful to think about the polar form. So any guesses about what my upper half plane turns into after I square it? So what happens when I square the polar form of the complex number r ei phi, or r ei theta? R becomes,
You get r squared and then
yep,
the constant in front of the I theta.
So I have ei theta, right? That's ei theta squared. So what does that give me? So don't let the I mess with you. The normal rules of algebra on exponential still works. So this becomes what actually?
It's a I 2 theta.
Yeah. Yeah, and you said it in a better way than I wrote it, so I'll do that. I 2 theta. Okay, so let's say that I took this point here, which is located at angle pi over 2. Where does that go after I square it, that point?
It'll end up in the third quadrant.
Right, so it goes from pi over 2 to 2 pi over 2, or pi. And what happens to this point, which is here at like pi?
The same, it'll go rotated by like 90 degrees.
So that one also double the angle?
Oh, I see. Yeah.
Yep, so pi to 2 pi. And then, if we want to talk about the radius, so points that are closer to 1 get shrunk towards the center, and points that are farther out, bigger radius than 1, will be stretched out. So there is a little bit of weird stretching. But the important part is that if I have some point here, which is, like pi over, I don't know, 6 or something like that, that's going to go to 2 pi over 6 or pi over 3, which I guess is more like there. So overall, what does squaring do? So when I square a complex number, what does it do to like some region of the image? So like fans it out like a deck of cards, right? So it takes every angle and it doubles it. So it does shrink points closer than 1 and closer than 1 to the origin. It stretches points farther out. But essentially what it does is it fans out some part of the pre-image so we fill the entire thing. Okay. So what if we had f of z equals z to the 1/2 power, or we had z to the 4th power, or we had z to the pi over alpha power, or something like that. So if you think about the radial part, what you can think about is, oh, this is what it's going to do. If it's positive, or sorry, greater than 1, it's going to fan everything out by that factor. And if it's less than 1, it's going to contract it by that factor, because that's what shows up in that, right? So we squared, so we got a 2 pi. If we cubed, we would have gotten a 3 pi. If we took it to the 10th power, we would have gotten a 10 pi, and we would have wrapped all the way around multiple times, which means we would have some funny issues, and we won't talk about branch cuts. But that's a really key insight in picking, just in general, where you want to go looking for a correct conformal mapping. Does that make sense? Okay, so I'm just going to drop this on you guys then. Do you guys want to solve an electrostatics problem or a ideal fluid flow problem?
Maybe a fluid flow.
Okay.
I don't know. Haven't seen one of those before.
So I want those titanium oxide smoke lines in my wind chamber, but I want them flowing into and out of a 45-degree corner. And you guys can 100% do this, and it will not take you a lot of math, but it might take a little bit of thinking. And this is how I'm going to define my corner. So that's a brick wall, and then that's a brick wall. And I'm going to start fluid coming in here. Obviously, it cannot pop through the wall, so it's going to come out. So any guesses about how I would do this? So in this case, really just got it down to 2 steps. Is let's write down an easy answer of a related problem, maybe fluid flow, just going past a wall, and then find a conformal mapping. So let's say I asked you to find the streamlines of a fluid that's just going like past a wall. And if you didn't see the whole fine print video, ideal means that there's like no viscosity and it's incompressible. So it doesn't matter if it's flowing next to this wall, it's just not gonna, it's not gonna interact with the wall in any sense, like no viscosity, no turbulence, no slowing down. So as the fluid flows, I guess the way that I drew it up there too, from right to left, what are the streamlines gonna look like?
They're just going to be kind of parallel to the ground, maybe.
Yeah, exactly. So my streamlines are going to be equal to just values of y is constant. Okay, and then what I'm going to do is I'm going to load this into a complex variable. So I'm going to declare z to be equal to this thing that ultimately I don't really care about. It's just kind of a placeholder for the harmonic conjugate. And I'm going to make the y values my streamlines. Okay, now that you guys know what you know, this is a valid solution. So this is a solution of the fluid flow past a wall if it's a viscosity-free fluid, ideal fluid. Tell me how to get from this to that. So I'm mapping the upper half plane into what, essentially? So think about compressing the wall itself or folding it. Oops, actually did that backwards. Should be left to right, not right to left, the way I drew it up there. Sorry. So if I wanted to make this wrap all the way around the upper half plane, I would square it. Let's say that I wanted to make it into a 90-degree corner. What transformation would I use? So from this, folding these angles in half, I would use f of z is, so I want to half the angle, right? So z to the 1/2 power, which is the square root of the radius, and then I theta over 2. So that's cutting the angle in half. So what conformal mapping gets me my streamlines for an ideal fluid that is going into a 45-degree corner?
Be z to the 1/4 power.
Exactly. So we have a mathematical worksheet. We can dump it in there to see. The problem is you have to, yeah, I don't know. It's up to you guys. We got like 20 minutes. So we would have to find u and v and then put them in the streamlines. So it's a little bit algebraic, but I promise you it's the correct answer. So this is it. So you just take lines of constant y, and then you say f of z is z to the 1/4. And then the lines of constant y that come out of this, so you put y equals constant in, what you get is streamlines of this 45-degree corner out. Okay, this is also the solution of a charged plate, the equipotentials of a charged plate, if I fold that into a 45-degree corner. So we got 2 for 1, actually. So does that make sense? Okay, that's good for corners and angles and spreading things out. And we saw one example of that. I showed you the squared one. But in general, what's going to happen for things that are like circular and funky is you're probably going to have to consult a table. And as I said, there used to be an amazing resource, a dictionary of conformal mappings, hosted by some smaller college. I don't know what happened to them, but I put the best I could find up in those resources. So let me show you how to use those, and then we'll do one last example. Either, let's see, we could do one with gravity, or we could do one with temperature, actually. So steady state temperature actually also solves the Laplacian, so that might be neat to see once. Okay, so W is the output and Z is the input. So what these show are two things. They show how the region transforms and how the constant lines transform. So what this is saying, so number 2 is pretty easy to see, is that if I have a constant line that's equal to this offset circle, the analytic transformation W equals 1 over Z is going to map this offset circle into a line located at 1 over a. So the line of z equals constant a is going to go after I transform that function into that. So if for some odd reason I wanted to transform an offset sphere into a parallel plate, which I don't know why I would do that, 1 over z could do that for me. Okay. Let me show you okay, this is the one that we worked out. So this should make a lot more sense. So what the transformation z to some power, and they're actually separating out the pi, so you can talk about just the angle directly. This will get you in between a parallel plate and an angle. So in this case, what you're doing is you're stretching the thing from an angle of alpha to the entire upper half plane. So all of the points inside of here will be spread out to the upper half plane. So that's the one we just did kind of manually. Okay, here are the two neat fun ones that you might see, logs and exponents. So exponent is one of the ones we use to do the end of the parallel plate capacitor or the end of a pipe. And what those will do is map regions like this. So rectangular regions to curved regions. So in this case, this rectangular region at the end of, so in the negative x, positive y, in quadrant 2 to here. And the points a, b, c, d are with primes shown in the image of that function. Okay. Logs are pretty neat too. So logs actually transform you in between. So this is more than you'll need for most problems. Usually what people do is just map a semicircular region. Logs will go the opposite way. They'll map circular regions to rectangular regions. So logs and exponents are really neat because they map circular regions to rectangular regions and the other way around. Right? And if you think about the polar form of a complex number, it should kind of make sense. So I'll just put these here. You can fish around and find them. The one that is on the homework is the airfoil one. So it's this really neat one that's just, and the question is essentially just implement that code and mess around with it. Okay, so we have 15 minutes. We can go through this entire process with a temperature problem. I can show you how equithermals actually also obey the Laplace's equation, or we can do a gravity one, I guess. And to be honest, the physics is kind of irrelevant. It's really just writing down the thing and finding the function that maps it into what you want. But I'll leave that up to you guys.
No, the equithermals sound interesting.
Cool. So we can do a thermal problem. So the first thing to do is and you guys have seen this at least in kind of a backwards way. I just changed the variables on the heat equation for that separation of variables problem on the last quiz. So this is the full heat equation. Yeah, I'll call it, yeah, no, I won't. Yeah, fine. So capital T is for temperature, lowercase t is for time. Kind of shame on me for doing that, but whatever. So this is the heat equation, and K is known as the thermal diffusivity. Essentially, how fast does heat make it through something? So K would be a really small number for brick or ceramic, and K would be a really high number for metal. So heat transfers really quickly through metal, really slowly through brick and ceramic. Okay. And what this is saying is essentially the spatial gradient of the temperature. So if I have a really big temperature here and I have a really small temperature there, I'm going to have a fast rate of change. But if I have a really small change in temperature in between points A and B, I'm going to have a really small rate of change. So that's the heat equation. Okay, so let's say that we, for instance, stick these two endpoints, A and B, at reservoir. So we fix A and we fix B by connecting them to, like a lake or an air conditioner or something that fixes their temperature. So now we say that these are fixed. And this is also fixed. So in that case, if you let time go for a while, this is eventually going to reach steady state. So the steady state heat equation and note that unless you're talking about just the super trivial case where this is equal to 0, like the or constant, everything's the same temperature. So this implies that we have heat reservoirs. To make the fixed temperatures. Is this. And you know what? In steady state, we don't even really care about K. So steady state heat equation is Laplace's equation. Okay. And honestly, that's the physics. So voila, it's just, this is the same thing as the streamlines for an ideal fluid or the electric potential for an electrostatics problem. All we have to do is put on the new terminology. Okay, so let's just solve a problem. So find the steady state temperature. For the following system. So we'll keep the upper part at 100 degrees Celsius. We'll keep the lower part at 0 degrees Celsius. TH and TL. And then we'll put some insulation on the sides. So all we care about is this rectangular region. Okay. So really what this comes down to is in the case of this temperature problem, what do I identify as the thing that becomes either the real or the imaginary part of the complex potential? So clearly it's T. So this is going to be the game plan, same as before, is find any T that satisfies the Laplacian make a complex potential. And then find a conformal map. So 1 and 2 are going to take a lot more effort than it seems is necessary to solve this problem. But the point is, once you do 1 and 2, you can just pick any conformal map you want and get the answer for any of them. Okay. So some of this stuff will be a little bit old news. So how do I solve this? So this is what I'm looking to solve. And t is a function of x and y. So we do this, all of this stuff for 2D problems only. So what I'm going to do is separate variables. And then I'm going to put this into del squared t equals 0, which gives me x double prime y plus xy double prime equals 0. And then I'm going to algebraically separate them. So all familiar stuff. So I get x double prime over x equals y double prime over y. And clearly this needs to be equal to a constant, right? So same game as you pick an x, I pick a y. We reveal them, they're always the same. Therefore, this is equal to a constant. Anybody want to guess about like a nice form for the constant? Sorry, there's a minus sign here. Because we got 2 derivatives. Turns out I'll make my life a little bit easier by calling that alpha squared. So we get the 2 ordinary differential equations. X double prime equals alpha squared x, and capital Y double prime squared x equals minus alpha squared y. Okay. So now the part where I actually care about the region. So here I go from 0 to 100. And here I have an insulator and an insulator. Well, so the x direction tells me that there is no derivative. So my lines of constant temperature are going to be equal to 0. Or sorry, my change in temperature as I go from here to here is going to be 0. So there is no change in x. Any x should have the same temperature profile whatsoever. So by the x symmetry, we get alpha equals 0. And then from, and x is constant. From the y equation, therefore, is, again, 2 derivatives of y need to be constant, but y itself can't be a constant because we got to get from 100 to 0. So y of y needs to be equal to ay plus b. So that is also something that has 2 derivatives vanish, but it will also get us from 0 to 100. And if you plug in the boundary conditions, you get that b equals 0 when y equals 0. We said this was 0 Celsius. What a really nice problem. So good boundary conditions, that would be whatever it is at y equals 0. We just made things really easy for this problem. And a is equal to 100 over whatever that distance is. So this goes up to some distance d. Okay, so we have this solved on some region. So what this means, therefore, is now for with one weird little side note. So we do need to find the harmonic conjugate. Once you find one solution of this problem, is that basically, again, anything that you do to it that's an analytic function is going to be okay. So 2 is find the harmonic conjugate for the t of x and y that we found. So we can make some thing that is a function, analytic functions map analytic functions to analytic functions. So we need to start with something that is analytic. So we do need to find the harmonic conjugate of t. And you guys know how to do that. I'll just do it really quickly. So du dx equals dv dy, where this is really dt dx equals d, whatever we want to call the harmonic conjugate. We'll call it phi, I don't know, why not call it phi, etc. So the typical way of finding the harmonic conjugate. And the harmonic conjugate, turns out, is 100 over dx plus some constant. So phi of x and y is this, and then t of x and y, its harmonic conjugate, the thing we found to begin with, is 100 over dy. And just because we set it up with t changing in the y direction, I think it makes more sense to turn that into the complex part. So lines that look like this are going to be our, if you stop somebody on the street, they'd probably not really know what you're talking about, but let's call it a complex temperature, because that's neat. And remember, the point of adding the harmonic conjugate is we needed to make something that's analytic. Okay, so it turns out that there's actually no conformal map required. We actually already have the solution. So that was just generating the first solution. Okay, this is the magic part, is that I want to, so we'll keep this as much of it as I can. So let's say that I wanted to do this. So maybe I have cold water going into like a centrifugal pump. So this might seem like a really funky temperature setup, but there is maybe something that could describe this. So I don't want to do that. So I have 0 degrees Celsius here. I have an insulator here. So the centrifugal pump is insulated. And then I have the heated up fluid going out the other side. So I have cold fluid going in one side, hot fluid coming in out of the other side. And I want to know the temperature, T of X and Y in this region. Okay, this is not an easy problem. And the steady state temperature would satisfy this. Okay, once we have our baseline solution, tell me how we do this, and then I'll ransack the table and show you. Again, this table is really awkward. There's a really nice one that I used to have. But tell me what I need to do, and I'll go find it.
If I remember right, you could take the solution to the rectangular kind of area and do a transformation where you say W equals e to the z on the z that we found there, and it would put it into a circular region.
Yes, so e to the z's turn circles into rectangles. The
Okay.
opposite goes the other way. So yes, it is log z. So it turns out that if I just take this, so we have conformal mapping that turns rectangular regions into circular regions, and we got to describe the points. So the point or this region turns into this region, and this region turns into this region, and then this region turns into this region. So I find whatever conformal mapping that is, and leave the red as red. So this is actually done by LNZ, and that's just me looking at the dictionary and finding the thing that turns rectangles into semicircles. So that means that the solution to this is we want the imaginary part. We put the imaginary part in, we get the imaginary part out. So we get the imaginary part of ln z, which is the imaginary part of ln phi plus it, which is the imaginary part of the natural log of 100 over dx plus I 100 over dy, which is the imaginary part of ln. Let's turn this into polar form, right? So this is 100 over d times x plus iy, which is the imaginary part of ln 100 over d rei phi, right? That's what x plus iy is, just changing it to polar form. And then a little bit of gross stuff. So obviously we're going to have some constant goo, but we have ln 100 over dr plus I phi. So this is all real. This is all imaginary. We have our outputs. So we're going to get something that I'll just try to sketch it. What you would get out of this is that you're going to get semicircular lines that go from 100 to 0, and they're going to decrease linearly as angle decreases. And that probably shouldn't be too crazy as a solution. So basically, if you're half the radians from here to here, it's going to be, surprise, surprise, 50 along the center line. Okay. And the part that is not obvious is how things change in the radial direction. So in the radial direction, like for instance, when I take a slice through here versus when I take a slice through here, instead of these lines of constant phi are easy, lines of constant r are not. So that would be given by this. So it would decrease by the natural log of the radius. Okay, so that was kind of quick. I crammed that in there. We probably would have spent maybe 10 more minutes explaining things more carefully. But the point is you have a base solution and you have a table of conformal mappings. You just dump it in. And then what you have to do is the interpretation in is the interpretation out. So here we had temperature as the complex variable. Here we have temperature as the complex variable. Any questions about any of that? So I'll post the Mathematica sample code. But yeah, that's really it. And again, I'm around for the rest of the week, beginning of next week for the The project stuff, interacted with 2 people pretty regularly. Hopefully everybody else is making good progress.